We can modify the Lorentz model to achieve other models for refractive indices describing various materials. One modification is a so-called Drude model. If the material has no specific resonances, we neglect the omega 0. The interaction of light takes place with free electrons and end up with the Drude model. This model still has some small damping part which restricts the movement of the electrons or ions. This small complex part results in both real and imaginary parts for the permittivity. And here we have an example of how the permittivity and the refractive index look like as a function of frequency. I have one important observation. The real part of the relative permittivity is negative below the plasma resonance frequency. Later on, we shall see that this feature enables very special guided modes that are called surface plasmon polaritons. When the respective refractive index is calculated, the region with negative permittivity results in refractive index whose value is below 1. A large imaginary part at this region shows that the optical loss is very high. The Drude model is often used to describe metals. As we see from the refractive index, the material is opaque at low frequencies, but becomes transparent at high frequencies, indicating the ultraviolet wavelengths in this case. Sometimes the Drude model is combined with the Lorentz model to end up with the, surprise, surprise, Drude-Lorentz model, which takes into account both the resonances of the material and strong contribution of free electrons. If the carriers have no damping, which is the case in dilute ionized gases such as plasmas, where we neglect the damping, in this case the imaginary part of permittivity is absent and its value is negative below the plasma resonance wavelength. The refractive index is 0 for negative permittivity, and large imaginary part displays high optical loss. So also in the case of free electron plasma, it is opaque at the frequencies below the plasma resonance frequency, but is transparent at the frequencies higher than the plasma resonance.